Okay, we're going to finish up chapter 4, and we're going to go from just knowing that molecules have covalent or ionic bonds and look at a very basic theory for how you can describe the bonding in those that have the covalent bonds. So we are going to talk about Lewis symbols and structures. Okay, so we're going to draw Lewis symbols for neutral atoms and ions. We're going to draw Lewis structures that depicts the bonding in simple molecules. So we know from last chapter that we can draw electron configurations for each and every atom. And when you do that with Lewis symbols, you just represent each electron as a dot. So the dots represent the electrons that it would be in the valence shell for those atoms. So sodium has that inner shell that's full. So we have that in brackets neon, but it has one more electron in its valence shell. So that's represented with a dot and a Lewis symbol. Same thing as you go down. Each and every atom as you go down has more valence electrons, so we have more dots. So essentially, you're representing which electrons will take part in bonding, because those inner shell electrons aren't important for bonding. So Lewis symbols illustrate the number of valence electrons for each element, and this is just for the third period. You could do this for any period. You can also represent Lewis symbols for ions. So when sodium gives up that valence electron, it becomes a +1 cation, and it no longer has any electrons in its valence shell. So there are no dots, and that electron has come off. And the same thing with calcium. It starts out with 2 dots, 2 electrons in its valence shell, gives them both up to form the calcium 2+ cation, and those 2 electrons are free. Anions are the same way. Chlorine starts out with 7 valence electrons, pick up 1 to give it 8 as an anion, and sulfur picks up 2 because it starts out with 6. And when it picks up 2, it has 8 as a 2- anion. And then when you represent how the ionic compound is formed, you just put those 2 cations and anions next to each other. So you have the Lewis symbol for sodium plus has no electrons. The Lewis symbol for chlorine as an anion, chloride, has an extra electron in it. So each of these is just representing how you would draw the structure that would be a Lewis symbol structure for an ionically bonded compound. Okay, so now we're going to talk about forming covalent bonds. So if you look at 2 chlorine atoms on the left sitting next to each other, neither one has the ability to pull electrons off the other one because they each have the same exact electronegativity. So the only way for them to get an octet is essentially to share. So when you find chlorine existing in the elemental form, it's always a diatomic molecule. It always has a single bond between 2 chlorine atoms. And so on the right-hand side, you are representing with a Lewis structure that those 2 electrons that weren't paired on each of those chlorine atoms can now pair, and in between the 2 chlorine atoms, you have a pair of electrons. And so if you think about it, those 2 electrons, each of the nuclei of the chlorine see those electrons and are attracted to them, and therefore they're attracted to the other nucleus, because nuclei don't attract each other, they repel each other. But by putting that electron pair in between, essentially you're putting some glue there. Okay, so this is 2 pictures. Now going from here where you're representing the shared electrons as 2 dots, here you're representing it as a line. So a single line is a pair of shared electrons. And these are just some other structures. So carbon tetrachloride, same thing. You can hook all of those chlorines on because each chlorine starts out with 1 electron and carbon starts out with 4 single electrons on it. And when they share, you get 4 single bonds representing those pairs of electrons with lines, and the same thing on the right-hand side. So we can look at lots of Lewis structures: ammonia, water, hydrogen fluoride. So these are just each pictures of those shared pairs of electrons that form the covalent bonds in molecules. Formaldehyde, ethylene. So we can have more than 2 electrons shared. Every pair of electrons that's shared is a bond. So in each of these, we have what's called a double bond, because the carbon and the oxygen in formaldehyde is sharing 4 electrons, and the 2 carbons on the right in ethylene are each sharing 4 electrons with each other. Carbon monoxide, you can go above a double bond and have a triple bond. So in carbon monoxide, the toxic gas for incomplete combustion, you'll have 3 lines, which represents you have 3 pairs of electrons shared between the carbon and the oxygen. Cyanide, which is extremely toxic, and it's also part of the process. It's used in the process to take gold out of tailings, and so you often get a lot of cyanide waste in tailings piles. But it also has a triple bond, so you have 3 pairs of electrons shared between the carbon and the nitrogen to give 3 lines, 3 bonds. So these are just some pictures showing Lewis structures. Nitrogen shares 3 pairs. That's why it's the primary component of our atmosphere. It's a very stable molecule sharing 3 pairs of electrons. Hydrogen sulfide has 2 hydrogens hooked onto the sulfur, and hydrogen bromide. These are just more pictures. I don't like to draw the pictures like this because, as you notice, they haven't included lone pairs, and lone pairs are going to be super important. So actually this slide is kind of one we should just skip. So this shows how you should write this structure on the right-hand side. You should write it with those lone pairs on the oxygen, because those are going to determine the shape of the molecule, which is going to be super important. And this shows you essentially why carbon and oxygen would want to share more electrons. So if you look at the left-hand side, that carbon in the middle is sharing electrons with hydrogen, so it sees 2 electrons, sharing electrons with each of the oxygens, so it sees 2 for each of those. So essentially it only has 6 electrons in its valence shell that it sees. And carbon likes to have an octet. It likes to have a full S and P subshell. And so in order to do that, if it shares another pair, it has 8 electrons that it sees. It sees 4 from the double bond, 2 from the single bond, and 2 from the bond to hydrogen. Similar to this picture, it's just once again showing you that when you have only a single bond on the left-hand side, oxygen and nitrogen both are deficient. They don't have an octet. Whereas if you share another pair, you can get closer to having an octet. You can't share 2 more pairs, because if you look on the right-hand side, nitrogen now has 8 electrons around it, and oxygen has 6, and it would be better if you could share more. But with that, yeah, if you shared more, no, you could still share more. It's going to show you a triple bond, yeah, in a second. I was thinking you couldn't because nitrogen would go beyond an octet. But yes, you can share even more. And now each nitrogen and oxygen has 8 electrons around it. A lone pair, those 2 electrons that aren't part of the bonding, and then sharing 3 pairs so that each sees 8 in its octet. Okay, so here are some more molecules. I guess I now understand what they were trying to do here. They were trying to show you how to complete the Lewis structures. So if we go through that same process, we're going to look at this example and complete the Lewis structure. So we need to put the lone pairs in. So first thing we did was draw bonds for everything to be attached. And then we give all of the terminal atoms all the electrons they need. Hydrogen just needs 2, everything else wants 8. So we gave 6 pairs of electrons to the nitrogen. And then we look at the central atoms. And so now we give the carbons and the nitrogen in the ammonia, the last molecule, a lone pair. But then we look at whether or not they have an octet. So when you look at the first structure with all the lone pairs around nitrogen, well, carbon only sees 4 electrons and it wants to see 8. So by sharing 2 more pairs from the nitrogen, now carbon sees 8 and nitrogen sees 8. And the second molecule, which is ethane, everything has an octet. Hydrogen never wants an octet, it just wants 2 because it's the only atom in the second period that'll form molecules, but are in the first period. But the first period is full when an s orbital is full because there aren't any p's. So it can only take 2 electrons in the hydrogen's valence shell. When you look at the third one from the left, you have the 2 pairs of electrons on carbon, but they still don't have an octet, so you have to share more. And by sharing more, you can get each to have 8 electrons. And on the far right, the ammonia, once we put that lone pair on there, nitrogen has an octet and each hydrogen has 2 electrons. Okay, so this is showing you the complete Lewis structures for carbon monoxide and carbon dioxide. So carbon with 1 oxygen and carbon with 2. Everything has an octet. And this is just insert for Richard Smalley, who was one of the fathers of nanotechnology. I didn't realize that they gave him the honor of being called the father of nanotechnology, but by discovering fullerene chemistry, so these molecules that are atoms of carbon with different shapes for the molecules, those can be used in different ways. They talk about using them for drug delivery because you could put something inside of it. So it was really the start of nanotechnology when they discovered the fullerene molecules. Okay, so this is an example of an electron deficient molecule. So nitrogen has 5 valence electrons, oxygen has 6. So you have a total of 11. When you put the single bond in, that takes 2, so you have 9 left. So if I put 4 or 6 on the oxygen and a lone pair and a single electron on the nitrogen, I can't do anything else because I can't create an even number of electrons. So we're not going to be able to give each an octet. It's called a free radical. But I can go from here and get them closer to an octet. If oxygen shares another pair with nitrogen, then nitrogen will see 2, 4, 6, 7. So we share another pair from oxygen, which gives nitrogen 2, 3, 5, 7, which is just shy of an octet. You wouldn't want to share another pair because then nitrogen would go over an octet and have 9, and that can't happen. So free radicals are situations where you violate this octet rule because you just don't have an even number of electrons. Another case where you violate the octet rule is with electron deficient. So beryllium only has 2 electrons if you look at its placement in the periodic table. In its valence shell, each hydrogen has 1. So beryllium hydride, you only have a total of 4 electrons. There's nothing you can do to give beryllium any more. So it's just electron deficient based on its location in the periodic table. Same thing with boron fluoride. Boron contributes 3. Each fluorine contributes 7. So you have 24. So you can make 3 bonds. That takes you to 18. And then all those lone pairs go on fluorine. we'll see with something called formal charges. If you were to double bond a fluorine, you would get bad formal charges. So this is the more stable structure. And from experiment, you can show that it's pretty much single bonds on all the fluorines is the more stable structure. And one of the things that's true about molecules that are electron deficient, so something like this boron fluoride, it would prefer to have an octet. So if it could react, for example, this molecule with ammonia, ammonia has that lone pair, it can then share that with the boron. And now when you look at the molecule on the right from that reaction, everything that wants an octet has an octet. Another case where you violate the octet rule is when you expand the octet. And that's only possible if you're beyond period 2, so beyond neon. If you're in period 1, hydrogen's shell, the 1, n equals 1 shell is full with 2 electrons. If you're in period 2, you have n equals 2, therefore you have L equals 0 and 1, which means you have s and p orbitals. So up to neon, all you have is room for an octet. But once you get beyond that, you can think that you also have d orbitals. So you have more places to put electrons. So these are 2 examples of what you call expanded octets, situations where the central atom has more electrons than an octet. More examples of that same thing. And how did we draw those? We drew them in the same way. Xenon would contribute 8 electrons. Each fluorine contributes 7. So you have 7 times 2 plus 8. You have 22 electrons. When you put in all the lone pairs, and this is cut off, you can see way to the far left and far right that each of those fluorines still has a lone pair on it. So when you take 2, 4, 6 for the lone pairs on each fluorine, you get 12, and then 14, 16 for the single bonds, 18, 20, 22. So you have to put those extra lone pairs on xenon, even though when you look at this, xenon now sees 2, 4, 6 for the lone pairs, 8, 10 electrons. So it had to go beyond the room it would have in S's and P orbitals to make this structure. Same thing for this one. If you add them all up, the xenon is the only place you can put more electrons, and you always put them on the central atom. But xenon has 2, 4, 6, 8, 10, 12 electrons for the bonds, and then 2 more, so 14 electrons in its valence shell when it's forming these kind of bonds with fluorine. Happens a lot with the halogens as well. So if you add up, for example, on the left-hand side, chlorine and bromine are both halogens, so they all contribute 7. So 7 times 4 is 28. And when you add this together, the chlorines have 18, 18 lone pairs, and then the bonds give it 20, 22, 24. And then bromine has to take those last 2 pairs to get up to 28. So both the iodine in this anion on the right, and then the bromine on the molecule on the left had to expand their octet to make these structures. So in order to think about what structures are the most stable, you want to think about how you compare structures. So you have different options. Probably the different option that was the most obvious was this boron fluorine one, where you could have easily put a lone pair being shared off of the fluorine with boron, and then you'd have one of those with a double bond. But we could figure out from formal charges that that would not be as stable. So we're going to compute formal charges for atoms in our Lewis structures. We're going to use those formal charges to identify the most reasonable, which is the same thing as saying the molecule that's probably the most stable. And then we're going to explain the concept of resonance and draw Lewis structures representing resonance forms for a given molecule. So here is an anion. And I would assume it's having you calculate the formal charge. Let's see if they give us the formula in one of the slides. Yeah, so they don't. How interesting. So when we look at each of the structures we can draw, we can look at which is the most stable. So when you look at carbon dioxide, for example, formal charge calculation never actually gives you the formula. The formal charge is essentially, you start out with, do a formal charge for each atom, and you start out with how many valence electrons that atom would have. And then you compare that to essentially how many electrons you put in its Lewis structure. So on the far left, this is going to be the most stable form for carbon dioxide. So if we look at each oxygen, oxygen has 6 valence electrons. And in this picture, I put 4 lone electrons around it. So I'm going to subtract those. So 6 minus 4 is 2. And then I have a double bond, which is 4 electrons. And I'm going to assume that that's shared equally, so that those 4 electrons are split equally between the oxygen and the carbon. And so 1/2 of 4 is 2. So 6 minus 4 minus 2 gives each of the oxygens a formal charge of 0. And then you can do the same thing for the carbon. Carbon has a valence electron number of 4. You put no lone pairs around it, but you did put 4 bonds. And so 4 bonds is 8 electrons. 8 electrons divided by 2 is 4. So the formal charge on carbon is 0. Whereas if you look at the other 2 structures where you put, well, the first one, we should be very careful. So the one in the middle is a resonance structure of the one to the far left, because I haven't moved atoms. So when you compare these 2 structures, 2 double bonds versus a triple and a single, we would say that the 2 double bonds is the more stable form, because we haven't pulled charges apart. So everything is 0. But if you look on the far right, notice now it's oxygen, oxygen, carbon. So this is a different molecule. So you wouldn't want to talk about the relative stability of these structures, because they're not the same molecule. Okay, but you can look at what's the most stable way for things to bond. So on the far left in this picture, the carbon's in the middle, the nitrogen's in the middle, and on the far right, sulfur's in the middle. So these are not resonance structures. These are different molecules, or different anions, sorry, because it has an extra electron. So which one is the most stable? So when we look at them and do that formal charge calculation, we get -1, 0, 0, -2 + 1, 0, and then we get -2 + 2 - 1. And so the one on the far left is the most stable, has the lowest formal charges. And this is asking the same question. So you could do formal charges for each of these to decide whether or not dinitrogen oxide is nitrogen, nitrogen, oxygen, or nitrogen, oxygen, nitrogen. So you could answer that question, which is the most stable, with formal charge calculations. And so that's what they're doing here. And so the one on the left is the most stable. You have to think about, it hasn't given the rules, which are in the book, so we'll talk more about the rules. You want everything to have 0 formal charge, and then you want the lowest formal charge. And then, for example, on the left, where you have +1, -1 for nitrogen and oxygen, you want to make sure that the element that's the most electronegative gets the negative charge, because if it's the most electronegative, it's going to have a better ability to pull electrons. And so we know that oxygen is the more electronegative. Therefore, the one on the left-hand side makes more sense based on who got the negative charge. Whereas over here, for 2 reasons on the right, it's not as stable. You have more charge separation, and oxygen, the more electronegative element, is positive, which doesn't make sense. That means it's pulling in a tug of war with nitrogen. It's stronger than nitrogen, but nitrogen wins and becomes negative. So that's the one that's more stable. Now it's asking the same question. We'll do more of these in class because I feel like actually putting the formula up will be helpful. And this represents that idea of resonance structure. So if you can draw more than one structure where you haven't moved the atoms and all you've done is moved electrons. So notice in these two pictures, they're equally stable because everything has an octet. On the left-hand side, you have a double bond on one side and a single, and then you flipped it. If you can do that, it probably isn't a molecule that has a double and a single, and you can figure that out with spectroscopy because one of those bonds would be harder to break, the double bond. And so it's a blend of those two. So you draw a double arrow to represent that you probably have a molecule that has about 1.5 bonds between the nitrogen and each oxygen. You don't have a double single, but because you can write these two structures, they're called resonance structures. And by putting the arrow there, you're saying that the true anion, NO2 minus, is a hybrid of those two. We call it a resonance hybrid. Same thing with this one, except now when you look at it, there are 3 different places for that double bond to be. So each of those bonds is probably about 1 1/3. So each of them is a single bond. And then that second bond of the double bond is being shared in 3 places. So the last thing we're going to talk about in this chapter is the idea of when is a molecule polar, and that's going to be based on its structure. And that's going to have, it's going to be very, very important. I mean, when you think about things like CO2, why does CO2 stay in the atmosphere for so long and create so many problems for our climate? First off is it's a very stable molecule, which we'll learn a lot about when we do thermochem. Second off is it's a very non-polar molecule, so it doesn't stick to each other or stick to anything else and condense. Whereas water is a greenhouse gas, it contributes to climate change, but it doesn't stay in the atmosphere very long because it's a polar molecule and it can go from the gas phase and stick in the liquid phase. So whether or not a molecule is polar is going to be super important when we think about its properties as a bulk system. So we want to be able to predict the structures of small molecules using valence shell electron pair repulsion theory. And all that means is that electrons are all negative, and so they want as much space as possible. They repel each other. So we're going to give the molecule geometries such that all those electrons around central atoms can be as far apart as possible because they repel each other. So we're going to explain the concepts of polar bonds and molecular polarity, and we're going to assess the polarity of a molecule based on its bonding and structure. So when we look at, this is formaldehyde, we can see from experiment that the bond angle between the hydrogens is about 118. The bond angle oxygen carbon hydrogen is a little bit bigger. Oops, they don't give you that angle. Well, but you could add it up. It's a little bit bigger. The bond length between the carbon and the oxygen is 1.21 angstroms. So it's showing you that with Lewis with a Lewis structure and VSEPR theory, we can get an idea of the geometry. This is showing you the big idea within VSEPR, which is beryllium is bonded to 2 fluorines. Each of those bonds is a pair of electrons, and those electrons want to be as far apart as they can be. So if that's all there is around the central atom, if you put those 2 bonds 180 degrees apart, that's going to be the best situation. And so this molecule will be linear for that reason. This shows you the best shapes to keep electrons far apart. So if you have 2 pairs of electrons, linear is the best, 180 degrees. If you have 3 pairs of electrons, 120 will be the best. If you have 4, it's 109.5. If you have 5, it's to put 3 in a plane at 120 and a pair above and below at 90. And if you have 6, it's to have them all 90 degrees apart. So that's just from geometry. So when we look at this structure, we have 4 regions of electron density. They're all bonding. And that means that this is going to be 109.5 degree angles within methane, which is also called tetrahedral. Okay, so now if we have ammonia, ammonia is slightly different in that if you look at it on the far left, A, 3 of the pairs of electrons are the nitrogen in the center bonded to hydrogen, but then it also is then left with a lone pair of electrons. And so it has a geometry similar to methane because it has 4 pairs of electrons, but we're going to name it based on where the atoms are, not the electrons. The electrons will help give it its geometry, but we name it based on where the atoms are. So this is going to be trigonal pyramidal. It's going to look like a pyramid. And the angles between the hydrogens are a little bit less than 109.5, because when you look at the VSEPR theory, lone. So if you have 2 lone pairs of electrons, they need more space. They're more diffuse. So their repulsions are greater than a lone pair sitting next to a shared pair or a bonding pair. And then shared are the smallest repulsions. So if you look at this, this is basically saying these angles should be about 109.5. They're a little bit less because that lone pair takes a little bit more room than the pairs that are shared between the nitrogen and the hydrogens. This is a table that I will give you on the test. It tells you the geometry and then for each of those situations with the number of bonding and lone pairs around a central atom. And this is just pointing out, it's hard to see. Let's go back here. If we look at this one at the bottom, I think it's easier. This picture is pretty hard to visualize for me. But if you look at number 5, you have a central atom E in this row, and you have different bond angles. So the best way to keep all the electrons far apart is to have a plane, and in that plane you put 3 of the pairs of electrons, so they can then all be 120 apart, and then you have a pair above and a pair below. So each of those can now be bonding pairs or shared pairs. So if we look at the sawhorse or seesaw, the best place to put the lone pair is to put it in the plane with all the 120 degree angles, because it wants more room than a shared pair. So in that plane, it can be 120 degrees apart from the other 2 in that plane. And then when you look at the next one where you have 2 lone pairs and 3 shared pairs, you're going to put the second lone pair also in that plane, and you get what's called a T shape. And then surprisingly, when you have 3 lone pairs and 2 bonding pairs, you end up with the situation on the far right of this line, where you actually end up with a linear molecule, even though there are lone pairs on that central atom, because all of those shared pairs would prefer to be in the plane where there's 120 degree angles with others in the plane. So that's the only situation where you have unequal angles. As you notice, linear is 180, trigonal planar and bent are angular. It's always the same situation in that those angles are about 120. For regions of electrons, they're about 109.5, but it's when you have 5 where you have some that are 120 and some that are 90, which makes you have to think a little harder. So carbon dioxide, double bond or single bond doesn't matter. They all need to be far apart. So you have pairs of electrons on one side and pairs on the other, and they have to stay together. And so the best shape for this carbon dioxide molecule is it to be linear. This will be 120. You have 3 pairs of electrons. This will be 120. This will be tetrahedral, 109.5. That's just showing you three-dimensionally how you represent. It's not a flat molecule like it appears here. So these dashes and darker line are representing that one of the hydrogens has to come out of the plane forward and one has to go behind the plane in order for that to be a four-dimensional molecule or cation, sorry, that has the three-dimensional geometry to keep those four pairs of electrons as far apart as possible. Water is going to be bent because if you look at it, you have four pairs of electrons, so it's going to have angles of about 109.5. It's going to be a little bit less because those lone repulsions are greater, but it's not going to be linear because if you made it linear, those two lone pairs would be too close together. This is just showing you that tetrahedral shape. This is just showing you essentially that lone pair on sulfur changes it from, it would be a tetrahedral geometry, but because of that lone pair, it is going to have the name. In the fifth line, it's going to be a seesaw or sawhorse. And this is showing you why. This is the unique one where it becomes planar. So it's a very symmetric molecule because all four of the fluorines will go in the same plane and the two lone pairs will be above and below the plane, which gives it started out with the very last one over here at the bottom with 6 pairs of electrons. In this case, 4 of them are atoms and 2 are lone pairs. Yeah, so we are in the middle here at square planar in that situation. And now you have to think that if you have other atoms in your molecule and you don't just have one central atom, you'd want to describe the geometry around each of these. So we'd want to start on the left and say, what's the geometry around the nitrogen? It will be about 109.5. What's the geometry around the carbon? About 109.5. Up here, this means that there's a carbon hooked to 3 hydrogens. So that makes that carbon hooked to 4 things, has 4. So it's also the tetrahedral 109.5. Then you get to the carbon with the double bond. That's going to be 120. And then the oxygen, we'll call that bent because it's just 2 atoms hooked on to the oxygen, but the angle will be about 109.5. So in order to talk about the geometry of a molecule that has more than one central atom, you have to focus on each of those central atoms and give that geometry. This is another example. You could go through that process. We'll do a lot of these in class. And now we want to talk about what makes a molecule polar. So it will be a very important property. So if you look at carbon and hydrogen, carbon has a slightly higher electronegativity than hydrogen. And so that's going to be a polar bond. Carbon is going to be slightly more negative and hydrogen left a little bit positive. Boron and fluorine is more electronegative. So the electrons are being pulled. The arrow is pointing towards fluorine. Boron is being left a little bit positive. But if you have more than a diatomic, so it's easy to say these are each polar. But if you have other molecules, so if we compare what I was talking about, why is it that CO2 does not form a liquid and water does at room temperature? Well, carbon and oxygen have different electronegativities. So when you look at the left-hand side at the carbon dioxide, each of those oxygens is more electronegative than carbon. So they're pulling electrons off of carbon. But if they're each pulling in the opposite direction, it's like if you were doing a tug of war and you had 2 clones on the ends and a person in the middle, you wouldn't move that person in the middle because you have equal forces pulling on on the opposite side. So because carbon dioxide is linear, essentially the same thing as saying those two vectors cancel each other. They're the same length, but they're going in opposite directions. But when you look at water, it's very different because of its geometry. So remember, water is bent because that oxygen has two lone pairs on it. So the angle should be something close to 109.5. It's a little bit less. But because those two, because it's bent, the vectors are the same length, but they're not pulling opposite each other, so they don't cancel. So overall, oxygen is slightly negative, and the hydrogens are slightly positive in water, which makes it polar, which makes it easy when it sees another water molecule for it to stick to it in a plus minus interaction. And that's why water can be in the liquid phase at room temperature. And so that's what this is showing. You can have a linear molecule. So this is just like carbon dioxide, except we've replaced one of the oxygens with sulfur. So it's linear, but the problem is sulfur isn't as electronegative as oxygen. So the vectors are going opposite each other, but they're not the same length. So you are going to end up with a dipole moment in this molecule. So in order to decide if a molecule is polar, you need to do its Lewis structure. Then you need to look at its geometry and the symmetry of the molecule. Here is just showing a picture of chloromethane. So you have methane, which we've already looked at the geometry is tetrahedral, but you replace one of the hydrogens with chlorine. Once again, chlorine is more electronegative than hydrogen, so its vector of electron pulling is bigger, even though they're in the opposite directions of each other. So overall, this molecule would be polar, and the slight negative charge would be on the chlorine. So same thing here. We have the geometry, and based on the geometry, we know that these molecules are bent for the left-hand side, the hydrogen sulfide, and for ammonia, the right-hand side, it's trigonal pyramidal. But because of those geometries, the vectors may be the same size, but they're not pulling opposite each other. So each of these molecules ends up being polar. And why is that important? Well, it's important for phases, like I've already mentioned. It's also important if you want to think about how you can separate things. So if you don't have an electric field and you have your sample in a solution, things are going to be pretty random in how they're oriented. But if you put an electric field in, so in this case on the right, you make it so that the wall on the left side is negative and the wall on the right side is slightly positive, then everything is going to orient so that the plus minus ends of those molecules are going to the part they'd be attracted to. So the positives will be attracted to the negative side, and the negative sides of the molecule will be attracted to the positive. So we'll talk more about that as we go into more detail about chemical reactivity. Okay, so this is just an exercise, which we can start doing exercises in class. Yeah, we'll look at, so these are just different exercises. I don't want to hook up a way to write on here right now. I think it's just easier to do the exercises in class. They have all the concepts in them that we've already talked about. So we are done with chapter 4. We'll do lots of examples in class.